In the last video, we looked at how to make Lewis structures. One thing we didn't address is what happens if we get to the end of those 5 steps and we've got more than one valid Lewis structure. This is the case when we run into things called resonance structures. All right? Now, the difference between resonance structures is we're only going to have our lone pairs and multiple bonds move around. So for example, if we look down here at the bottom, we have these 3 resonance structures. We can just kind of ignore this red circle for now, just pretend that's not there, right? What we do see is that in this molecule right here, in this Lewis structure, we've got a single bond between the nitrogen and the carbon. Then we're going to move one of those lone pairs over, and now we've got a double bond. Right? Now, in order to not violate the octet rule around carbon, where carbon only gets 4 bonds, never more than 4 bonds around carbon, we needed to move one of those multiple bonds, one bond out of the triple bond over onto the oxygen. So now I have a double and a double instead of a single and a triple. All right, we can move one more over and one more over, and now we've got that triple and a single. So all of these have the same order of attachment. They've got the same number of electrons, and everything has an octet, and I've used up all the electrons. So which one is best? And that's what we're going to look at here. So let's talk a bit more about what resonance structures are. Let's look at ozone. All right, now ozone, O3, ozone layer way up high in the atmosphere, helps protect us from UV rays. We can draw it in 2 different ways. Now these look really similar, but for the sake of argument, let's label these oxygens O1, O2, and O3. All right, now in structure 1 here, I'm going to have a bond between a double bond rather, between O1 and O2. And in structure 2, I've got a double bond between O2 and O3, right, oxygen number 3. Right, these are both examples of resonance structures for ozone. All right, now which one is right? Well, actually the trick is that neither one individually is correct, because in reality, ozone's kind of a blend of these 2 molecules, right, these 2 Lewis structures. All right, we don't have a double bond and a single bond, which if we sort of drew it out to scale, if we had a double bond and a single bond, we'd expect to have a short bond and a long bond. Remember we talked about bond order. The higher our bond order, the shorter our bond length. And that's not what we see in ozone. We actually see 2 equal length bonds. So what's going on? The trick here is to recognize what resonance structures actually represent. Right, now we can think about the resonance structures in one way as sort of moving back and forth. You say, well, what if it's just sort of switching back and forth? The location of these lone pairs, right, that we see right here, right, this lone pair is going to kick over and give us this double bond. Right, this double bond is going to kick over and give us a new lone pair. And we just sort of move things back and forth. And maybe it's just happening really, really fast. And that's why the bond lengths are, in essence, equal. But that's not quite good enough, right? It's not just that it's moving one way and moving the other way, right? So individually, we do have these 2 resonance structures, and this is a really good tool for looking at and explaining what's going on. We can have these 2 possible structures, but in reality, what we end up with is a blend. All right, we call that blend of our resonance structures our resonance hybrid. All right, now to think about this, I want you to consider the difference between a blue horse, a red donkey, and a purple mule. All right, now if you know something about colors, if we add blue and red together, we get purple. And if you know anything about animal husbandry, okay, a bit more of a stretch, if you take a horse and you cross it with a donkey, you end up with a mule. Right? Its own separate animal with its own characteristics. All right, so a mule. What is a mule? Is it sometimes a horse and sometimes a donkey? No, it's always a mule. So a hybrid is an equal blending of these traits. Just like purple isn't sometimes blue and sometimes red, it is its own thing all the time. It's a blending of blue and red. One of the things I like to do in class is say, okay, who else can think of a hybrid? And inevitably someone says something like, oh, we got those Prius cars. They're hybrids. No, they're not hybrids, because the way that a Prius works, or a hybrid motor vehicle, is it actually does go back and forth between a gas motor and an electric motor. But it doesn't do both at the same time. All right, so it's one thing and then it's the other thing. That's not what we're talking about. A resonance hybrid, just like a mule, is all resonance structures at the same time. So really what we have is we have to combine these two to get to our average resonance structure, right? Our resonance hybrid. So let's take a look at what that means for ozone. Now, we combine this together, we first write down all the things that never move. So I've got my oxygens, I've got these 2 lone pairs on the end, I've got 1 lone pair in the middle, and I've got those sigma bonds, so those single bonds. All right, we'll come back later and we'll talk about sigma bonds as a word I just said. It's coming up in the next chapter. But for right now, we'll just say they're those single bonds that we've got hanging out between the oxygen at the end and the oxygen in the middle. Now what's left are these dotted lines, and these dotted lines here represent the double bond that is sometimes there versus the extra lone pair that is sometimes there. All right, actually here we'll circle the one at the end since that's the one that looks like it disappears from structure to structure. All right, in essence what we're saying is, hey, sometimes this pair of electrons here, sometimes it's here. All right, sometimes this pair of electrons here, and sometimes it's there. All right, so we have those 2 dotted lines. All right, so what does that mean? That means that this pair of electrons is delocalized. It kind of hangs out over this entire central area. All right, so that electron, that pair of electrons, is shared over those 2 bonding areas, right? One between oxygen 1 and oxygen 2, one between oxygen 2 and oxygen 3. So the hybrid is what really exists. And in the case of ozone, my 2 resonance structures are completely equal, right? They're equivalent to one another, so we get a 50-50 split between the 2 of them. Let's take a look at some more examples. Now, what is delocalization? All right, well, delocalization or localization is the idea that electrons either exist in one place, right? So specifically between 2 atoms, as we talk about right there in what I've already written, right? Versus delocalized, where you are shared between at least 3 atoms, right? So a few adjacent atoms. Here, my delocalization, like I said, occurs in that area, right? And the dotted line helps show that. Sometimes in resonance structures, you'll see a solid curved line drawn instead. So you might see something like that. That's a little more confusing at this point, so we're going to stick with the dotted lines, right? But you will see those perhaps as you go on through organic chemistry. That's sometimes used as symbology. Right, now this helps us explain those equivalent bond lengths. Right? Now when we looked at ozone, I sketched out, oh, we could have, this short bond and this long bond, a bond order of 2 and a bond order of 1. But instead what we have are 2 bonds that are equal in length and somewhere between a double bond and a single bond in terms of length and strength. This is because our bond order for ozone happens to be 1.5. Right, now how do we get that? Well, we say, all right, how many bonding areas do I have? I've got 1, 2 bonding areas. And how many total electron pairs are in those 2 bonding areas? I got 1, 2, 3. That's where we get 3 electron pairs that are in the area, and we have 2 bonding areas, or 2 bonded atom pairs, right? 2 areas where bonds show up. So 3 pairs of electrons, 2 areas, 3 divided by 2 gives us that 1.5. So this is where we get our fractional bond order, right? So it's somewhere between a bond order of 1 and a bond order of 2, which falls straight in the middle, which is where we end up with those bond lengths and strengths that are somewhere in between a single bond and a double bond. All right, we said we'd do some more examples. Here's our next one. Let's take a look at the nitrate ion, NO3-. All right, now we're going to shortcut the beginning of this. We did Lewis structures in the previous, so what do? We're going to say, all right, first I need to figure out how many electrons I have. I got 1 nitrogen, 3 oxygens, and 1 extra electron because it's an anion, so I get 24 valence electrons. We put our nitrogen in the middle because it's the least electronegative atom. We build our skeleton, we put our lone pairs around the most electronegative atoms, and this is what we end up with when we run out of electrons. All right, if we count it off just to double check, we've got 2, 4, 6, 8. We got that in 3 places. 8 times 3 is 24, so we are good, but unfortunately, nitrogen is missing an octet. So we got to fix that. So how do we fix that? Step number 5, we're going to bring in one of these lone pairs down into the middle. Let's do that on the next page. We got a bit more room. All right, so see here, I've got that same structure that I started with. I said, all right, nitrogen here in the middle doesn't have an octet. So I'm going to I'm going to move one of those lone pairs. I'm going to start over here actually on the left-hand side, and I'm going to move that into the middle. Right now, there's nothing magic about moving it from the one there, so we could say, oh, well, what happens if I took this lone pair and I moved it down, and I brought those back out? Now I've got a double bond going up to the top, and single bonds to each side. All right, and there we have there. But again, there's nothing special about that one. Why don't we bring this one in and kick that up? Notice I've got these bidirectional double-headed arrows. And now I've got a double bond on that right-hand oxygen. Right, now I could keep going round and round in circles, but I would just end up back over on that side. So these are the 3 resonance structures that we can build for nitrate. One double bond between each nitrogen and each oxygen. What does our resonance hybrid then look like? Right, our resonance hybrid is going to first have all the things that are always there. I always have a nitrogen in the middle, and I have a single bond to each one of these oxygens. What else is always true? Each oxygen always has at least 2 lone pairs. Like that. All right, now sometimes it's got a double bond, sometimes it doesn't. So now we draw those dotted lines. Like so. So right here is my resonance hybrid, and it's got a negative charge. A negative charge up there as well. What does this mean for my bond order? Well, again, how many pairs of electrons do I have? I've got, let's pick my middle resonance structure here. 1, 2, 3, 4 pairs of electrons. And how many bonding areas do I have? Well, we think about the overall bonding areas. I got 1 area, 2 areas, 3 areas, 3 bonding areas. 4 divided by 3 gives me a grand total of 1 1/3, right? Or, you know, I'm not going to be too sad if I wrote 4/3 for my bond order. Either way. So that's going to give us not only how we draw the individual resonance structures in brackets with my charge out here outside of it, double-headed arrows separating each resonance structure. I can get my resonance hybrid, which we see down here, and then we have our bond order. All right, we'll do some more examples like this. Let me know if you got questions.